Okay, today's lesson we're going to look at starting our new unit, which is on nuclear physics. And the first chapter that we're going to look at is dealing with the atomic structure and different models that occurred over time to sort of explain how the atom and electrons are arranged. We're going to go back to J.J. Thomson for the first model, but before we get to that, the early theory about atoms came from John Dalton, and he basically thought that atoms were solid pieces of matter that couldn't be broken down any further, and we often call it a billiard ball model, thinking like an atom is like a pool ball, that it is what it is, it's the size and shape, whatever it is, and nothing can be changed. Obviously that's no longer true, and J.J. Thomson was sort of the first key guy to show that it was actually quite a bit different. Most of his work dealt with cathode ray tubes, which remember is just a tube with a charge plate separation in it, and we try to get charged particles to move across it. And most of his experiments had to do with electricity and magnetism and things like that, but we learned a little bit about electrons and charges in the process. So a few other guys here did some more work on cathode ray tubes, but it's not that important. We just want to stick with what J.J. Thomson kind of came through. So he had three experiments that sort of changed things a little bit. The first was he tried to separate the negative charges from the positive charges using electric and magnetic fields. And obviously he couldn't do that because we now know that all of the charges in a cathode ray situation are electrons. It's the electrons that are moving between the positive and negative plates. So because he couldn't separate them, he then deduced that when the charges went from a positive to a negative plate, that it had to be an electron. So he said, well, in these situations then it's only electrons that are moving, so obviously we can't separate them from any positives. He then tried to see if he could deflect them in an electric field, and he proved that that works. So he took the electric charges that were traveling in the cathode ray tube, and he saw that they deflected towards the positive plate. So therefore, once again, they had to be electrons. And the last experiment was, could he get them to be deflected in a magnetic field as well? And he did that, and basically saw that the electric force and the magnetic force could be balanced. So this diagram is a little small, hard to see, but let's zoom in a little bit. Oops. Okay, so we'll zoom in and we'll just scroll down. So in this experiment, he heated up electrons. He then sent them through a charged plate to accelerate them. And then once they went through the charged plate, he then put them through an electric field. So you can see here the negative plates on the bottom, positive on the top. So the electrons are going to move upwards, so our electric force would be upwards. Then he also had a magnetic field into the page, which would mean the magnetic force would be downwards if we use our left-hand rule. And he just adjusted those two electric and magnetic fields. So the idea is if you only had the electric field on, the electron would move up towards the positive plate and it would curve upwards. If you only had the magnetic field on, it would go downwards. If you had them both on, they would kind of cancel each other out, and if it was set just right, he got the electron to go straight across. And it's that process that he basically used to figure out what the velocity of the electrons are. So he took the electric force formula, so we know electric force is EQ, and he took magnetic force, QVB, that we used in the previous units, and he basically made those two forces equal to each other, because if the two forces are balanced, our electron would go straight across. So we get QE equals QVB, the Q's cancel, we can rearrange it, solve it for velocity, and we get electric field divided by magnetic field. So that was his first key result, was being able to figure out the velocity of the electron if the two fields were balanced. We often call that the velocity selector formula, because he selects the electric and magnetic field and balances them so that you end up getting a velocity. So he knew that it was just the electrons, and he could figure out what speed they were going at. So this first example is just saying calculate the velocity, so we just go electric field, 7.62 to the 7, and divided by the magnetic field. And that'll give us our velocity in meters per second. And we get an answer of 2.09 times 10 to the 7. So quite fast. We're dealing with about a tenth of the speed of light. So pretty quick electrons being accelerated here. After that, he then said, well, what happens if we take the electric field off? We have just magnetic. And if we remember from a previous unit, if our electron's traveling that way and our magnetic force is downwards, we know the electron then it's going to travel in a circular path due to that magnetic force always pulling it inwards. So in that case, we can take our magnetic force, QVB, make it equal to circular force, mv squared over r, and we can rearrange and solve it for whatever we want. But back in Thomson's time, he didn't know the charge of an electron, and he didn't know the mass of the electron, so what he basically did was solve for both. He just said, well, let's solve it for charge to mass. We know the velocity, we just calculated in the previous example. We know the B field, and we can calculate the radius easy enough, so we just need to figure out what the charge to mass is. And he called that the charge to mass ratio. So let's do this example. So charge to mass would be V over BR. So we have, first thing we need to do is figure out that velocity. So electric field over magnetic field. So we get 1.86 to the 4 divided by 5.80 to the negative 4. If we do that calculation, we get an answer of 3.2 to the 7 meters per second. So now we can plug that into our charge to mass formula. So 3.2 to the 7 and divided by magnetic field again. And the radius, which they tell us is 0.325. So if we do that calculation, we get a charge to mass ratio of 1.7 to the 11. And that would be coulombs per kilogram. Okay, so that's the number based on those calculations. So now it says, actually, let's compare this to the accepted value. So we know now that the charge of an electron is 1.6 to the negative 19, and we know the mass of an electron is 9.11 to the negative 31. So if we actually divide those out, we get 1.76 to the 11. So you can see the numbers are pretty much the same. So after Thomson figured out the whole charge to mass thing and identifying that it's electrons moving in a cathode ray, that was a pretty big deal. So what Thomson then concluded was that the electrons have to be separate, and he wasn't sure sort of how they would be separated. So basically what he thought is they must be pretty small and they must be pretty densely charged to be able to hold the charge. So then what he thought of is that the electrons then are just randomly inside of a positive fluid or a positive chunk of material. So we often call it the plum pudding model or chocolate chip cookie model or anything like that, where you kind of see the negatives are just randomly scattered throughout the positive material. We know this is wrong, but he was sort of the first to sort of identify that negatives and positive charges are separate within the atom. And that's all.